Welcome back to Physics Fundamentals. In this video, I want to introduce you to Newton's laws. The ideas we're going to be discussing here are the ones that were introduced by the British philosopher Isaac Newton in his textbook Principia Mathematica, which was published in 1687. On one hand, that was quite some time ago, right? 450 years at the time I'm filming this. Coming up on that. On the other hand, in the grand scheme of recorded history, it's practically a blink of an eye. This textbook, essentially, the Latin title roughly translates to the mathematical principles of natural philosophy, are the framework on which all of physics has been built. Prior to this time, the dividing line in all of academic study was quite a bit blurrier than it is today. You had poets and you had philosophers. That was it. You were one or the other. Philosophy included the branch of natural philosophy, which is what we would today call science. And even within that, meteorology, optics, ecology, geology, kinematics, and chemistry all kind of fell into this one basin. And we were only starting to tease apart the fact that there were differences between the ways we could study the natural world. And Principia Mathematica is kind of the foundation that led to physics becoming its own thing. So all of physics kind of boils down to Isaac Newton's work. In that work, Isaac Newton proposed 3 laws of motion. The first is called the law of inertia. An object in motion will continue moving in a straight line, and a stationary object will remain stationary until the object interacts with some external force. I've seen many ways of phrasing the law of inertia. A lot of scientists really still love to quote the translation, "A body in motion remains in motion, and a body at rest remains in rest." It all means the same thing. Language has evolved over the past 450 years, and Sir Isaac Newton was writing in Latin in the first place, so there's no one definitive way of stating it. The first law tends to bring up a very important question. What is an external force? Well, that's what the second law answers. The second law is the law of acceleration. And the law of acceleration is almost always given as the equation F equals ma. We've dealt with A already. A is the acceleration under which the object is undergoing. We've talked about m. I don't remember if I've used the variable m for this previously or not. I believe I have. M is the mass of the object, and then capital F here is the force acting on the object. Working in one dimension, this isn't that big of a deal, but I do want to, for continuity's sake, remind you that acceleration is a vector quantity. It can mean positive or negative values when we're thinking in one dimension of accelerating to the left or to the right, or maybe it's up or down. Negative mass is nonsense. Mass is always a scalar value. And it turns out that when you multiply a scalar times a vector, the result always works out to be a vector. So force is a vector quantity. We have more to go before I start trying to use this formula as part of problem solving. But I like to introduce it pretty early on because in a lot of ways, this is the definition of a force. A force is something that causes acceleration. And we measure force by multiplying the mass of the object times how much it is accelerating. Before we do any problem solving, I want to think a little bit about units. We know that mass is typically measured in kilograms, sometimes grams certainly, but kilograms is far more common as a standardized unit. And we've seen that acceleration is given in meters per square second, which all told is just a massive pile of units. Kilogram meter over square second. And scientists decided that kilogram meter over square second, even though that is absolutely valid and absolutely describes what a force is doing, is just too much to write down. So we invented a shorthand for it, the letter N, which is an abbreviation for the unit of Newton. Lowercase n because this is a unit. It's named after Isaac Newton, but it is not his name, so the unit of Newton is lowercased. The variable, or the symbol for Newton, is capitalized. It's confusing. You will make mistakes on it. I won't correct you. I'll probably make those mistakes as well. So we have a very interesting unit here. We have a new unit, which is what we call a derived unit, right? The Newton isn't one of the metric units, but it goes into the SI system anyway, because trying to deal with kilogram meter over square second is just too messy, and having a nice simplified version of that just makes life a little bit easier. All right, so before we continue on to problem solving, let's round out Newton's laws. I said that there were 3 laws of motion. We got through 2 of them. Now on to the third, which is typically called Newton's law of reaction. The classic translation tells us that every action has an equal and opposite reaction, which I guess makes sense, or makes something resembling sense or something. I don't know. The terminology definitely is no longer there anymore. If object 1 exerts force F12 on object 2, then object 2 exerts force F21 on object 1, where F21 is equal to the negative of F12. Remember that forces are vectors. Positive and negative is perfectly valid. But let's try to make a little bit more sense of this by thinking about a person pushing a box. If the person applies a force on the box, then there will be an equal and opposite force pushing the person back. You have almost certainly experienced this at some point in your life. You were leaning against the wall, you pushed the wall, and the result was that you were standing upright. A much sillier example, which makes it a lot of fun, imagine being on a frictionless surface. Imagine you're standing in the middle of an ice hockey rink. With all of that ice around, you can't really move. But you're standing next to a box, and you push the box towards one end of the rink. The result of you pushing the box is going to result in you sliding away from the box. The box will slide one way, you'll slide the other. That's what we're talking about when we talk about equal and opposite here. That's what the law of reaction is telling us. In everyday life, we don't really experience that, right? If you're trying to push a sofa down the hallway, you're able to push the sofa and keep going because you're also pushing on the floor, and the floor is providing friction, which is adding to the total force. But if you've ever had the misfortune of trying to push a sofa down the hallway where there was a loose rug instead of installed wall-to-wall carpet, and the rug just started slipping out from under you, you know that bad things can happen in these situations. All right. How about a couple of examples? A 20-kilogram crate is resting on a frictionless surface. You pull on, the crate with 500 newtons of force. What is the acceleration of the crate? And I've drawn a figure over here. Going back to what I was talking about in that previous example, in order for you to pull on the crate, you had better be on a surface that has friction. Otherwise, you'll just pull yourself to the crate as much as you'll pull the crate to you. So you're standing off of a sheet of ice, holding onto a rope that is wrapped around the crate you're trying to move. You pull on the crate. Maybe you are just using your hands. Maybe you are using a winch. I don't really care. But in some way or another, you're applying 500 newtons of force. All right, so let's dive into some problem solving. We're dealing with forces, so I am immediately writing down Newton's law, F equals ma. And then I'm going over to the left side of my page. I'm writing down F, I'm writing down m, I'm writing down a. In the problem, we're given that the force is 500 newtons. Notice the decimal point there, which tells us that the ones place is significant. We're given the mass as 20.0 kilograms, and the acceleration is our unknown. So we're going to have to solve for acceleration first. Rearranging this formula is fairly straightforward. Just flip the left and right, and then divide both sides of the equation by m, and you get that acceleration is force divided by mass. I've talked about this previously, but I'm going to repeat myself because no one ever believes me. Right? In a classroom environment, you don't really get the value of taking the time to rearrange the equation for the variable you care about first, because we're in a time crunch and we're trying to get through as many different ideas as possible. That's not how the world works. If you are going on to study something intensively, going on possibly to a graduate education, or if you're going onward to a career where you have to do quantitative work of any sort, you're going to solve the same problem over and over again. So taking the time to rearrange the formula and get it in a form where you can plug in the numbers, you can plug them into a calculator, the calculator will spit out an answer, and you don't have to do any thinking, is key. So we take the time and we do that here, even though it doesn't give us the value because we're probably not going to reuse this formula that much. That's okay. It's a skill worth developing nonetheless. All right. And then from here, we can just plug in our numbers. 500 newtons, 20 kilograms. My calculator is very happy to tell me that if I take 500 and divide by 2, if I take 500 and divide by 20, I get 25. I guess it's going to be 25.0, so I still have 3 significant digits. And then I have to think about units. Newtons per kilogram is the same thing as newtons times 1 over kilogram. And remember that a newton is a kilogram meter over square second. Sometimes I swear they come up with these derived units just to make your life more difficult solving these problems. The factors of kilograms cancel each other out, leaving behind meters over square seconds, which is exactly what we expect to get when we are trying to calculate an acceleration. It's never a bad idea to go through and make sure your units work out, although if you feel confident in your ability to do the algebra and you know what the units should be when you're done, I'll admit that I won't notice if you just jump and say, well, I know it's supposed to be meters per square second because it's an acceleration, so I'm just going to write it down and cross my fingers and hope for the best. 99 times out of 100, that works. The things that you can be careful of, though, double checking and deriving your units will give you a chance to make sure that you didn't miss anything as far as doing unit conversions. Everything is in the units you expect for the formula. And going through and double checking the units is a great way to double check your algebra. If you made a mistake somewhere in the problem, if you got values in the wrong places, if you rearranged the formula and something weird happened, the units won't work out. And it's a sign to you that you did something wrong and you should go back and you should try again. All right, one more example, and it's seriously not as bad as it seems when you look at this giant wall of text. A rocket engine operates by pushing out exhaust at high speed. The force needed to do this, in turn, causes the rocket itself to accelerate. And then I have 3 questions here. First, if 95 grams of exhaust particles are accelerated by 2,500 meters per square second, how much force is acting on the exhaust? From that, you should then be able to calculate how much force is acting on the rocket. And finally, if the mass of the rocket is 22 kilograms, how much does the rocket accelerate? I'm going to copy just the first question here so that I can take it to a clean space and start working on it. And then we'll come back for the other parts a little bit later. All right. So we're talking about a mass, we're talking about acceleration, we're asked about a force. It looks like we're going to be using Newton's second law here. F equals ma. We're asked what the force is, that's our unknown. The mass is given to us as 95 grams. And grams aren't a useful unit here. We need kilograms in this formula. So we do the conversion and we get 0.095 kilograms. And then the acceleration is 2,500 meters per square second. Plugging those things into the formula, being thankful that the formula is already solved for the variable we are looking for. And then rounding to, it looks like we have two significant digits here. We get about 240. I have kilograms multiplied by meters per square second, and a kilogram meter per square second is the unit of a Newton, so we have force units, which is exactly what we hoped for. All right, so that's what we're asked for in part 1. Or I guess it was part A. Now let's go back and grab part B and continue onward. I'm not sure what happened over there on the side of the page. I just won't worry about it. How much force is acting on the rocket? This one is very straightforward once you realize what it's asking. The law of reaction says that if the rocket is applying a force to the exhaust, then the exhaust is applying an equal force to the rocket in the opposite direction. And the force acting on the exhaust is 240 newtons. Let's go ahead and call that E, the force acting on the exhaust. The force acting on the rocket is the same magnitude, opposite direction, so negative 240 newtons. And then if we come back up one more time and go ahead and grab part C here, and put it on the correct page. No. That took far more time than I care to admit. It would have been faster to just rewrite it, but you didn't have to experience it because of the magic of video editing. If the mass of the rocket is 22 kilograms, how much does the rocket accelerate? We have the force given to us right there. We have the mass now given to us. The force was negative 240 newtons. The mass is given to us as 22 kilograms. The acceleration is what we are asked for. And Newton's second law tells us that F equals ma. And we've rearranged this previously to get that A is equal to F over m. So we plug in. $240 newtons, 22 kilograms. We grab our calculator. And I guess I have two significant digits here. I get my acceleration is 11, and I know that newtons over kilograms is still going to give me meters per square second. We've done that already once in this video. Interesting consideration here. A rocket that's 22 kilograms is going to be a relatively large model rocket. All right, so something about the size of me, honestly, but skinny tube, big old rocket engine at the bottom, and it's going to accelerate upward at 11 meters per square second. Comparing that quickly to gravity. We know gravity is trying to accelerate downward at 9.8 meters per second. This is slightly more than that, so the net acceleration is going to be upward, the rocket is going to go up into the sky, although not particularly quickly. But going up at all is absolutely a victory. I hope that that problem gave you some insight into what we are talking about when we talk about forces. We'll have more to play around with on that. We'll have more examples of particular kinds of forces coming up in future videos. A lot of the rest of this class is just looking at forces of different sort. But for now, I think that's plenty enough to do in one video, so I'll wrap up with that. As always, thank you for joining me, and I'll see you in the next one.